Right, continuing to recap syntax for first-order logic, otherwise known as predicate logic. We are going to do parse trees, variable scope, and sentences. Kind of three ideas that are all more or less conglomerated into one. So first is parse trees. So when we're evaluating parse trees, what we overall want to do is evaluate what the main connective or quantifier is. Here, it's this exists y. So we're going to just get rid of that and take what's ever left behind. That's for all x pz, or there exists a z such that for all x qxx. Next up, we have this disjunction as the overall connective, because we remember that we treat quantifiers basically as like negation in terms of priority. So the next thing is this disjunction. So we'll split off into for all x pz, and there exists a z such that for all x qxx. I should keep my x's there. On the left-hand side, we now only have one quantifier and no connectives, so we have a very easy choice of what to keep splitting on. This has to go down to pz. And on the right-hand side, we have one quantifier as like the main one, so that's also a pretty free choice. So this will go down to for all x qxx, and then finally qxx. And once we have these predicates acting on objects here and here, we consider these to be sort of like propositional. Like we think of them like propositions in essence. They can't be broken down any further. We're basically just asking, do these objects satisfy this property? Okay, so that's how we would draw the parse tree for this formula. Because we could draw the parse tree, we know that it is a well-formed formula. We can get it by applying the rules to these predicates and objects, and eventually work our way back up to the formula. So we know we have a well-formed formula, and the next thing that we want to ask is this a sentence? And so the way that we do that is we kind of look at the quantifiers. So where did we apply quantifier rules? This very first one applied exists y, which means that everything beneath that has y within scope. So here y is in scope, here y is in scope, here y is in scope. All of these formulas have y in scope. Great. Where else do we have variables in scope? Here we did a disjunction, and that's not quantifying a variable, so we don't look at that one really. Here we did remove this for all x, and that means that every child of it has x in scope. So just looking beneath that quantifier, everywhere beneath it has x in scope. Finally, we go over to the right-hand side. We have this exists z quantifier, which means that we can then continue down and check z is in scope here, and all the way at the bottom, z is in scope here. So continuing on this line of reasoning, we only have one other place that a quantifier is introduced, but when we construct our things going up the parse tree, and that's right here. So here we introduce this x, which means it's quantified there. So x is also quantified here, and there's no other children of that quantifier. So we now know for which formulas in the end resulting formula we have quantifiers in scope. So now we can kind of go through and match these. So this for all x, it's not actually quantifying any x's here. We can go down to the other side. We have qxx. There's no quantifiers there. X will eventually be in scope when we work our way back up. And here is in fact where we introduce this. So these x's are what we call bound. So if your variables fall under the scope of a quantifier, we call them bound, and if they do not, then they are called free. So for all x qxx, these x's are bound, but for qxx, these x's are free. Continuing up here, we then introduce this z variable, and this z variable isn't actually quantifying anything. I mean, it's quantifying z, but z doesn't appear anywhere in the formula, so we don't really evaluate it at all. Continuing our way up here, this x is still bound because it was before. These x's remain bound all the way up, in fact. And as we keep looking through here, these remain the only things that are bound. And so we might notice some strange things here. This y never bound anything, and here we quantified over z, but we didn't actually, and we, in other places, used z, but that z never got bound by the actual quantifier. And so the difficulty here is that we need to be very careful about how our parse tree is structured, because that tells you where things are actually in scope. The last thing that we can do with this exercise is to look at what are sentences and what are not. So a well-formed formula is a sentence if every variable is bound. So sentence if and only if all variables are bound. So this here, these x's are not bound, as we talked about earlier. So we would say that this here is not a sentence. Here, when we go up a level, we quantify over the x's, and they're appearing in the formula, and there's no variables that are not bound, namely, there's no free variables here, so this would qualify as a sentence. Continuing up here, this formula. We have this z, but this z is setting up the bounding for the variables, and it never actually appears in it. So everywhere that the z does appear, it is bound, because it doesn't appear in this formula outside of the quantifier that introduces it. So this is a sentence. Continuing on the other side, we have this is not a sentence because z is not bound. Here we quantified over x, but our variable was actually z. And so since those two don't agree, we get that this is not a sentence because z here is unbound. If we take a disjunction of something that is not a sentence and something that is a sentence, well, this z doesn't change its boundedness. It is still not bound, and so this is not a sentence. And finally, when we go up to the very top here, this z remains unbound. And so even though we're quantifying over y, z is still unbound, so this whole thing is not a sentence. Okay, so that's a lot of analysis of one formula. We looked at whether subformulas were sentences, we looked at whether this overall was a formula, and we talked about bound and free variables as well as variable scope.